molar property of the I component is defined as du by dni, d, and all the mole numbers other than I being kept constant. So there is a C component mixed here. There are C partial molar properties that can be defined. What we saw and what is important also is to see how, for instance, this can be written as n times, because we can still need homogeneous states. So the extensive property can be written as a total number of moles times the corresponding specific property. N is here. So it's also useful to express the partial molar property in terms of the representation given here, in terms of the specific, corresponding specific property and the derivatives of the specific property with respect to their own fractions, right? So then that leads to the following formula, which is given by u, that is a corresponding specific property, plus du by dzi, where I am referring to this representation, minus sum over j equal to 1 to c minus 1. This is valid only for I equal to 1 to c minus 1. The c partial molar property, the partial molar property, the c component will have a slightly different form, and it will have, just it will not have this term. So this will help you to, given you know there are two options. One is, suppose let's say we are given this, that is specific property expressed in terms of the temperature, pressure and motion fraction. Then one way to calculate the partial molar property would be to directly apply these formulas. Another way is to convert this to the corresponding extensive property and express it in terms of the temperature, pressure and mole numbers, C mole numbers, and then use this formula. This is easier to remember because it is the same for all components. It's very easy to remember. You just have to take a derivative of the mole number of the I component. Whereas this is a bit difficult. Even given the formula, it's a bit difficult to apply correctly. So you have to choose which one you want to do. Right? So then closely related are the so-called Gibbs-Duhem equations. And I write them only in the form in which the Gibbs-Duhem equations in terms of the mole fractions are given by sum over j equal to 1 to c zj d dzi equal to 0. Sum over j equal to 1 to c, each of the mole fraction times the corresponding partial molar property, but derivative with respect to z I said there will be only c minus 1 of the Gibbs-Duhem equation. If I write in terms of mole numbers, then you get c Gibbs-Duhem equation. They are equivalent to these, and you have two different forms of the Gibbs-Duhem equation in terms of the mole fractions. The derivative is the extensive property with respect to the mole fraction. That I am not going to write. You can add that to the list of equations. Now, when it comes to representing, in terms of figures we saw, for the binary mixture at least, it's easy to represent because there is only one mole fraction. So it's always conventional to express in terms of the mole fraction. This I want to express. You have to be in terms of mole numbers. Right? The mole numbers themselves do not have a great significance. So mole fractions that determine the partial molar properties strictly. Right? So we saw that there is the other way of representing the data, and that is in terms of delta, which is defined as mu, and if you want I can put this as a mixture mu. This is is a specific property. There is a change in property on mixing, and that is given by U of the mixture minus sum over j into 1 to c uj zj. The uj is the pure component specific property of component j. Of course, it could be a function of temperature and pressure. Now, when you come to binary mixtures, it's important to understand there are some limiting features here. This is valid for general also. You can easily show the limit of zi. What is easy to illustrate in terms of the binary mixture. Let's now consider the binary mixture I and then c is equal to 2. So first thing you see is that you might have noticed the figure that either you can represent, so for a binary mixture Z1 is the only independent variable apart from temperature and pressure. So whenever you see a representation, let's say we saw some figures for the H versus Z1, so only one independent. So that means automatically means that the temperature and pressure are fixed, and this diagram corresponds to a particular temperature and pressure. And as the temperature and pressure changes, the diagram will also change. If nothing is given, that means you are being asked to find the partial properties at some temperature and pressure which might or might not be specified. But that you have to know that these are also functions of temperature and pressure. Sometimes you don't realize that because it is sort of suppressed and you're given the data at a particular temperature and pressure. You ask to generate the whole set of relations for a particular temperature and pressure. But now, either you can plot this or you can plot this. There is a change on mixing. You will see that we saw some figures like this, for instance. And we also saw some figures like this. The important thing to notice is that if you are plotting this, you can easily show that the endpoints have to be 0. So this is Z1 equal to 0, 1. So this is going to be pure component 2 and this is pure component 1. The value of the change in property due to mixing will simply be 0. And to see that, we see here that U mix minus U1 Z1 plus U2 Z2. And of course, this can be written as sum of j into 1 to 2 Zj Ujpm minus U1, let me write it fully then, Z1 U1 Pm plus so let's take the limit as Z1 goes to 0. The limit as Z1 goes to 1, let's say, pure component 1. So we take that limit. So Z1 goes to 1 means automatically Z2 would have to go to 0. Right? So this term will vanish and that term will vanish. So we are left with Z1 times U1Pm minus U1. You can also see that this is an important property of the partial molar property. Because there are many ways of checking your answers. We are given an expression for u and you are asked to calculate the partial molar properties. One way to check your answer is to verify if this is satisfied. Another way is to see if the Gibbs-Duhem equations are satisfied. One quick way to check is if the limiting conditions are satisfied. So clearly, limit Z1, what we get here, or Zi going to 1, this is in fact valid very more generally. Because when we are going to the case of the pure component I, it is valid for even a C component mixture. So binary mixture also it is valid. That in the limit where all the other components mole fractions are becoming 0, that means we are going to the limit of the pure component I or 1 or whatever it is. Then the corresponding partial molar property has to go to the corresponding specific property of the pure component at that temperature and pressure. with that you will clearly see that since U1 Pm goes to U1 and Z1 goes to 1, this will become 0. Similarly, you can show that limit Z2 goes to 1 of this would be 0. That's why when you have the change in property of fixing plotted, the endpoints are automatically determined. Of course, when you're having H mix, depending on the choice of the 0, it might also, one of them might also be 0. But let's say it has a form like this. Now, what can you say about these quantities? What would this correspond to? This is Z1 equal to 0. What would this correspond to? This value at the end point of the H. This is now the H mixture, the specific enthalpy, not the change. It will be the it's not partial, it is pure. When the pure is there, there is no partial molar. So what is it? What does this represent? This value here represents the specific enthalpy of pure component 2. That's very important to understand. That many, because Z1 equal to 0 means it is pure component 2. So what you are having on the left is the specific, this is actually H2 and this would be H1. Whereas if you are plotting the change in enthalpy and mixing, the two endpoints will be automatically 0. Let us now take an example. Take an example, the one which is not there in the assignment sheet. We will work out the quantitative expressions. Now take this. The H of the mixture is now given by, just what you have on the assignment sheet is slightly modified. This is how it is given. It's very important to know that the fact if it is not specified whether it is a binary mixture or not. Now this is the way the equation is given. I picked it up from one of the standard textbooks. So they would have automatically said that this is a binary mixture. If it is not said it's a binary mixture, it could very well be a ternary mixture. But for a ternary mixture, x1 and x2 are the only independent variables. However, for various reasons of convenience and so on, even for a binary mixture, knowing very well that only one of the mole fractions is independent, sometimes you see this kind of a representation. So let us now specialize these equations for the binary mixture. That is something that you have to do. So now the point is to calculate H1 Pm and H2 Pm. Right? So first I need to know for a binary mixture, how would this look like? This would be H. Here the mole factors are given in terms of x1 and x2. dH by dx1 minus what is the sum amount to. How many terms you will have in the sum? Only one term, right? So minus x1 dH by dx1. So now by writing this, I am automatically choosing x1 to be the mole fraction of choice because there are two mole fractions, x1 and x2. I can choose any one. The way I have developed all the notation, it automatically, so you should not get confused. Certainly if you take x2 as the mole fraction of choice, then the whole thing would change, right? So what I am pointing out that you are given two components, let's say ethanol and water. Now whichever, if you want to express in terms of the mole fraction of ethanol, right? Then what I am saying is that choose one to be ethanol and then use the formula. That choice you always have. Now let us say no, if you want to express it in terms of mole fraction of water, what I would say is choose water to be the component 1 and use all the equations rather than getting confused. Right? So you have to make a choice, which in the binary mixture there is choice only one mole fraction. I am calling that as Z1 in here. So if you only Z1, it has to stop here. Now if you're given ethanol and water, you can choose the mole fraction of ethanol to be Z1 or the mole fraction of water to be Z2. I'm not constraining you that you have to choose in a particular way. You call that Z1, whatever you want to express in terms of, you call that as Z1 and proceed. Right? That way you are less likely to make a mistake. So H2PM, here again is given as 1 and 2, so I am going by x1. H minus x1 dH by dx1. So very important to remember, I am reading the partial because actually with respect to temperature and pressure. But this whole thing is again at a fixed temperature and pressure. So I can, for all practical purposes, just directly differentiate. But this does not mean keeping x2 fixed. That is absurd. So when differentiating with respect to x1, then x2 is also changing, right? So that's very important to keep in mind. So if I want to avoid making a mistake, I have to now write everything in terms of x1. So let's do that. Another way to do it is that keep it as a function of two variables x1 and x2. But remember that whenever you are differentiating with respect to x1, remember to differentiate x2 also, and remember then that dx2 by dx1 is equal to what? Minus 1. You can do it that way also. You find it compulsory to write everything in terms of 1 minus 2. Keep it as x2, but you have to differentiate. Whichever way is convenient to you, you can use. The final answer has to be the same. You can retain x2 for convenience, but make sure that you differentiate that also. Just saying that I am differentiating with respect to x1 does not mean that x2 is kept fixed. That will defeat the whole purpose. Right? So I am going to do it this way. So all I have to calculate is, this can be further written as h plus 1 minus x1 dh by dx1. X1 is the only variable here. This is all at a particular temperature and pressure. So dH by dx1 is 500 minus 1000, right? Whereas I can then write 50x1 plus 40 times 1 minus x1. And then I can differentiate that with respect to x1. So that's x1 minus x1 squared. So that will be 1 minus 2x1. Plus x1 times 1 minus x1. Now I have to differentiate with respect to x1. 50 minus 40. So all I have to now do is to gather together all the terms. So I have here so I have to do that. So 5 minus 5. So let me write the answer if I have it, because it's just a question of now algebra, not even differentiation. So let me just, if I have it ready, I write out the answer. So it's going to take some time to do it. So dH by dx1 looks like it is going to be minus 460 plus 60x1 plus 30x1 squared. And just check, this is going to be minus 500. That is one term, which is minus 500. So I have a 50 here. And then a 40. Check that. Oh, 50 won't come in. So there's only the 40 that looks like okay. So let's go proceed with this. Right? So you have to gather together all the terms. Best would be to correct, all the three terms: constant, x1, and x1 squared. You just have to expand the whole thing and gather together. You can certainly, in an exam, you can very well make mistakes in this because it's somewhat cumbersome to do it. So you have to be very careful in doing this. Once you have got this, right, so I have got this. So let's now again H1Pm would be H, which is all of this, right, minus plus 1 minus x1. Again it's going to be a big headache to gather together all the terms. So I'm not going to again do it. So the final answer is what I am going to write. It is 540 minus 60x1 plus 20x1 cubed and H2 Pm, that is the partial molar. The second component is 1000 plus 30x1 squared plus 20x1 cubed. Because the whole point is once you have got dh by dx1, let's just gather together all the terms and doing the algebra. I don't want to spend time doing that. You can easily verify that. And let's now check the limiting quantity. First, let's look at this, right? As x1 goes to 0, what do you get? You get x1 goes to 0 means x2 equal to 1, right? So h is equal to 1000. As x1 goes to 1, h is equal to 500. So what does this correspond to? 1000. Let's say units, take it as some joule per mole or kilojoule per mole. Or maybe kilojoule is too much, joule per mole. So what does 1000 corresponds to? 1000 joule per mole. What H does it correspond to? H2, right? It's the pure component. Second, pure. So first, because as I said, once you've done all the differentiation, gather together terms, and there is all this scope for going wrong, at least you can check if your limiting values are correct, right? So let us see. Now, as x1 goes to 1, h1Pm should go to h1. So as x1 goes to 1, I get 540 minus 60 plus 20, which is 500. So we are getting that limit. So that is it. Could happen that you made mistake in 2 of the terms and somehow they are cancelling and you are getting the right answer. So it's not an absolute guarantee, but in a quiz or an exam and you don't have time, at least this is very easy to check. Rather than going through the whole manipulation, at least then you can have some confidence. Then this is what I want to check. You should know what to check. Right? What I want to see is as x2 goes to 1, that is as the pure component 2 be reached, then h2Pm should go to h2. If you are looking for the long limits, then you will again, there is no point, it defeats the whole purpose of doing it. So when x2 goes to 1, I have to express everything in terms of x1. So clearly, I have to put x1 equal to 0. So the value is 1000. It is again matching with h2. So it's good. It is likely that these answers are correct. Right? Let's now look at the other limit. What we get, right? Limit x1 going to 0 of h1Pm is what we are getting is 540. This is often referred to as the partial molar property of component 1 at infinite dilution. So another quantity defined in most of the books. This is now x1 going to 0, h1Pm, won't go to h1. So it goes to some value. It is defined as the partial molar property corresponding to infinite dilution of component 1 in 2. So we are basically taking a pure 2, adding some 1 to it. It will give the infinite dilution h1Pm will give how much the enthalpy will now change. That's roughly the way you should interpret it. So this is the effect of changing the enthalpy by adding small amount of pure component 1 to 2. This is how the enthalpy will change. Now we can also calculate limit x2 going to 0, h2p. So this is the infinite dilution of component 2 in 1, and then when x2 goes to 0, that means x1 should go to 1. The answer is 1050. Right? We can relate it to any quantities here, but it represents the change in enthalpy that you would get by adding a small amount of 2 to a pure 1. Right? That is the meaning I can give to it. Right? So these are some limiting quantities. Now, so this can be regarded as method 1. You directly use the equation. Another method would be that, let us say you don't have access to these equations. The easiest way is to convert it to write the exercise method 2. Method 2 would mean I will write H, that is the total enthalpy of the mixture expression of N1 and N2. I am not going to do that, so I will do H, and the whole thing I have to multiply by N. Right? So first term would be 500 N times x1, so that would be 500 N1. Plus 1000 N times x2 would be 1000 N2. Right. And then plus, here you have to be careful. So let me write it down. 50, best way is to write it as 50 N1 by N1 plus N2. Plus 40 N2 by N1 plus N2 times N1 N2 divided by what? Divided by x1 and x2 times x2, what would it become? N1 N2 divided by N2 squared. That is there. Yeah, let's first write that. N1 plus N2 squared times, because I have N is still there. These two terms are multiplied already by N. That I have to, yeah, what you are saying is correct. Net result would be simply. So if you went like this would be 500 N1 plus 1000 N2, right? Plus 50 N1. That's going to cancel 40 N2. N1 N2 by N1 plus N2. I hope I've done it correctly, not missed out any. So this I am cancelling also. That's why I put that there, because everything. Oh, have I made a mistake? Let me cancel it here. So let me cancel it here. So what you're saying is let's write the full. Does this make sense now? You can now verify whether it is correct or not. The important thing to check is that whether the homogeneity, because I have seen some expressions in some books where they empirically fit the H or V to some expression, doesn't even satisfy basic homogeneity properties. So there you go and see if the Gibbs-Duhem equations are satisfied, you will find that it is not satisfied. So that might be good. Empirically it might work, but you should, even if you are doing an empirical fit, that's when you will see this kind of relations. Why you have x1, x2, something, how do you arrive at this expression? First of all, you see that the linear term takes care of the limiting value. The other terms, purely an empirical method, no rigorous how it should be fitted, but this polynomial fit seems to be very famous or very common in fitting the partial molar properties or the mixture properties. First thing is to check whether H, anyway this is dP, is fixed, whether this is satisfied. That will not only tell you whether the original expression is correct or whether any of the original expression given to you is correct. If you have made any mistakes in, like I did earlier, in missing out some of the end terms, right? That will, is it verified? Is this satisfied? Is the first thing you have to check. Right? It looks like it is satisfied. Lambda times n1, lambda times n2. Here I have a square and this is a cubic. Right? So again, lambda squared you will get in the denominator and lambda cubed in the numerator. Those will also cancel and I will get lambda as a factor. So that's the first thing to check. Right? When you have the expression. Then I can go and I leave it as an exercise for you to figure out. Now you do dH by dN1, keeping N2 fixed, you will get H1 dN. You can figure out for yourself which one you find to be easier to apply. You apply this in terms of the mole fractions or convert it to in terms of mole numbers. Now there is a third method. It cannot be distinctly called a method, but there is a method 3 which depends upon method 1, which is often used in some of the books, and that is that once you have got H1 partial molar property of component 1, you use the Gibbs-Duhem equations to get the other partial molar property. So what the Gibbs-Duhem equations says is that it puts a constraint on the partial molar properties. Because if I have C components, then I have C partial molar properties, I have C minus E which is constraining them. Right? So it is not all independent of each other. So it is very easily seen in the case of a binary mixture. So we see that only one of the partial molar properties, so we have only one equation. Let's now write the Gibbs-Duhem equation for the two components, binary mixture. So again, you have to very careful to put J equal to 1 to 2. So it means Z1, Du, so the sum is over J. I have only one equation. I is equal to 1 because I have chosen Z1 as my defining variable here. Right? Again, notation is very important. Z1 du 1 dm by dz1. Again, here the partial refers to not giving Z2 fixed but giving the temperature and pressure fixed. That's why I am retaining. Sorry, Z1. You can see. This only gives you an equation. So what this means is that if I know one of the partial molar properties, then I can get the other one rather than using this. I can use the Gibbs-Duhem equation. Now, when you have given this, this doesn't really help that much because I have already determined dH by dx1 and I can easily go and calculate H2 directly. However, some books also have problems and there's one or two or like that in the assignment. Suppose you have given, I give you just H1 PM and I ask you to find H2 PM for a binary mixture, then you have no option but to use the Gibbs-Duhem equation. So let's do that, even if we already have the answer. So here I need to write this as just changing the notation. This is what we have, and I'll show how to find H2 PM from the H1 Pm that I have found here, which is 540 minus 60 x1 plus 20 x1 cubed. So I get x1 times, now I have to differentiate that with respect to x1. So I get minus 60 plus 60 x1 squared. Plus 1 minus x1, again I want to work only with x1, right? So 1 minus x1. This of course I don't know. So that's what I would say, leads to a ordinary differential equation in H2, which I have to now integrate to find the H2. But you get an integration constant. So even though there is a partial sign here, I treat it as a constant because everything is at a fixed temperature and pressure. It is constant with respect to that temperature and pressure. Right? So that's what you have to understand. So now I can easily write this as minus 60 x1 times 1 minus x1 squared plus 1 minus, so I can cancel one of the factors. So this would be minus 60 x1 times 1 minus x1 to cancel. So 1 plus x1 is equal to minus d. So I do very easy to integrate. So minus sign can be cancelled. So this 2 is equal to 60 x1 squared by 2 plus 60 x1 squared. I will now integrate. Right? So that would be 60 x1 cubed by 3. So that would be 20 x1 cubed. So I can make it 30. Plus a constant. Now the constant, how do you determine the constant? Differentiate with x2. Constant, I don't have to find it. When we differentiate with x2, x2 constant will disappear. So where am I going to find the constant? Answers are here. Yes, limit. What limit you would apply? x1 goes to 0. That is pure component 2. So limit x2 goes to 1 of h2 Pm is equal to h2. So if I were to give this problem, if let's say if I give this, then you can easily find h2. If I don't give this at all, I could just give a problem with just h1 is given, h1 Pm is given, right? Then I ask you to find h2 Pm. Obviously, I have to give the value of h2. You see here, one of the problems in the assignment sheet is very similar to that. If you check problem 7, benzene cyclohexane mixture, you are given the V1 Pm. So you are asked to find V2 Pm to a cyclohexane. And you are given the density of cyclohexane is 0.768 grams per centimeter. This is very good. This is a specific volume. Density is given, you can easily find the specific volume. This is the mole per mole I have to find out. So I should know the molecular weight of cyclohexane. So that's how it is given. So what is given there is V2. Must be given, otherwise you will have to deal with the constant, you have to leave it like that. You cannot determine it fully. So here I know H2. So if I were to give you this problem, I will probably give you H1 Pm, not give this at all, and then give you the value of H2. Then you can find it. So this is equal to H2. So X1 goes to 1 is X1. So H2 is equal to constant. So the constant is actually equal to H2, and that we have already found to be 1000. So I can replace this by 1000, and we can now verify what you will get. 1000 plus 30 x1 squared plus 20 x1 cubed is what I get. You can have to verify that even this I didn't do fully. You can verify that this is exactly what you will get by applying the equation directly. for H2, partial molar property of H2. You can also get it, right, with the Gibbs-Duhem equation. So this is the utility. So what the Gibbs-Duhem equation? For a binary mixture, if you know one of the partial molar properties, you can get the second one by using the Gibbs-Duhem equation. It might be so. Let's say experimentally you don't find, right, one of the partial molar properties, or that information you have available, and you want to find the second component partial molar property, you can use the Gibbs-Duhem equation. That's one advantage. Or another way is if everything is given, then you want to check whether these results are correct. Then you can substitute it into the Gibbs-Duhem equation and verify whether it is satisfied. That way you will definitely verify the answers you have found are correct. Are there any questions? Yes? Yeah, H is the mixture. So it should also represent the pure component properties in the limit. That it should accurately represent. So I am taking the limit. This is H mix. X2 going to 1 should give me H2. Limit X1 going to 1 H mix must give me H1. That is the pure component element. So the mixture represents the entire range starting from pure 1 to pure component 2. Right? So it has to respect that, otherwise it is not valid in the limit. So when I give you some expression for H mix, it includes the pure component properties also. If it doesn't, then it is not valid in the limit, and I have to say that it is not valid in that limit. So you no longer depend on that, and that has to be given separately. Right? Let's say I obtain a fit only in a narrow range, let's say 0.2 to 0.7. So obviously there I cannot put x2 equal to 1 or x1 equal to 1 and expect to get the pure component. Normally when you are given these, it is understood that it takes care of the whole range. Nothing is mentioned. Then you can assume, and I guess all the books assume. Yes, that will answer your question or not. Okay. Any other questions? Now these expressions that you have, let me take that out separately, also give a very nice graphical interpretation to the partial molar properties. Let's say I have here. Now you can clearly see, let's say in this case, if I were to plot this, the limit 500, x1 goes to 1, it is 5. So pure 1 is 500, pure 2 is 1000. I'm going to plot x1. So this H mix. So if I don't say mix, it is H. H represents the mixture. Now when you tell me how the H is it going to be monotonically decreasing, or will it go through a maximum or a minimum, is certainly possible. The answer again is here in the board, on this board. Can you tell me by looking at it how is it going to have a maximum or a minimum, or is it going to vary monotonically, that means decrease all the way from 1000 to 500? Decrease all the way, how can you arrive at it? Derivative is x1 is always less than 0. Throughout, it may not always happen. Right? But delta makes certainly it has to go through a maximum or a minimum, because the ends are 0. So it goes through a maximum, then it will be positive. Enthalpy change on mixing is positive. It goes through a minimum, that is enthalpy change. So that doesn't say anything about how the H mix is going to perform. Right? So here in this case, it's very clear that it is this. So now if we take a particular x1, right? So since I have dh by dx1, right? So since all of this corresponds to a particular temperature and pressure, I can interpret the partial derivative as simply the slope of the curve. Right? So now if I take the derivative, so what does this correspond to? This clearly corresponds to h. Right? So let's now take the slope of the, that is the tangent. Geometrically I can draw the tangent to the curve. So assume that this is the tangent. the tangent to the curve, run out of time, but I give you the interpretation. The tangent to the h mix versus the exponent of this value only for the binary mixture, because I can get a nice plot on a two-dimensional plot. You can easily show me this is x1 equal to 1, this is x1 equal to 0. This intercept that the tangent or the slope to the h versus x curve has at any point, right, will give me, so this is x1, let's say x1 star. That is a particular value of x1 I have chosen. You draw the tangent, and then wherever it intercepts the x1 equal to 1, it can be easily shown that this is h1 pm at x1 star. Wherever it intersects the x1 equal to 0, that means the x2 part of the axis, this intercept of the slope can be easily regarded or it can be shown to be x2 pm evaluated at x1 star. So that can be shown from these equations to prove that is but you can easily verify that what I am saying is correct or not. Because once the slope is there, then you can calculate what these distances are and find out how this interpretation whether it works or not. So simple rule geometrically is draw a slope at any point, and whatever point you want the partial of it, wherever it is intersects the x1 equal to 1 line, that intercept is the partial appropriate component 1, and wherever it intersects the here it goes to the partial appropriate component 2. So you have to take this up in more detail in tomorrow's class because we run out of